Hello, welcome to this video. In this video, we'll be looking at rates of change, which is an application of the chain rule. Now, rates of change are basically how fast or slow a particular quantity increases or decreases. Now, different quantities are interrelated, and so given the rate of change of one, we would like to determine the rate of change of the other. And we shall use the chain rule and the particular relationship between the two quantities to get what we want. Now let's look at this example so that we can illustrate just that. So we have that the side of a cube is increasing at the rate of 6 meters per second. Find the rate of increase of the volume when the length of a side is 9 centimeters. So basically, if this is our cube, if we call the side length x, we know that dx dt, that's the rate of increase of the side, the length of the side, 6 centimeters per second. So we can write this as 6 centimeters per second. This is dx dt, the rate of change of x with respect to t, time. Now, what they want is dv dt, the rate of increase of the volume. How do we know? We know that v is equal to x cubed. And from the chain rule, you can see that dv dt is going to be dv dx times dx dt. This we get from the chain rule. So basically, to get dv dt, we need dv dx, and dv dx would come from an equation that relates v and x, which is right there. And then we need dx dt, which has been given in the question. So from this equation here, we know that dv dx is 3x squared. So this is going to be 3x squared times 6 centimeters per second. But so this would be 18 squared centimeters per second. But the question was asking for when the side length is 9 centimeters. So dv dt, x is 9 centimeters, would be equal to 18 times 9 squared. Now this will be in centimeters cubed per second. And the answer here is 1,458 centimeters cubed per second. And so that's how we use the chain rule to calculate the rate of change of the volume when the length of the side is 9 centimeters. Have this equation and then look for the equation that relates the two quantities. You usually be given one rate and then be tasked to find the other. Let's look at another example. The area of a circle is increasing at the rate of 3 centimeters squared per second. Find the rate of change of the circumference when the radius is 2 centimeters. So we're being told that the ADT is 3 square centimeters per second. And what is wanted is CDT, where our C is the circumference. Okay, is there an equation that we can use to directly relate the area and circumference? Maybe not, but we know that area is equal to pi r squared. And so the ADR is 2 pi r. Okay, can we use the ADR to find the RDT? Well, we can, because the ADT is equal to the ADR multiplied by the RDT. Now, let's come to the side of the circumference and see what we need. We know that circumference is equal to 2 pi r. And so the CDT is equal to, sorry, the CDR, the CDR is equal to 2 pi. So if we have the CDR, we know that the CDT, which is what is required, would be the CDR times the RDT. Now we have the CDR, so we need the RDT. But we can get the RDT from this equation right here. Because from this equation, if you rearrange it, the RDT would be equal to the ADT divided by the ADR. And so that means that the CDT is going to be the CDR times the ADT divided by the AD, the ADR. Now the CDR is 2 pi, the ADT has been given as 3, and the ADR is 2 pi R. And so that means the CDT is going to be 3 out of R. Of course, this is now going to be in centimeters per second. The units will be centimeters per second. Let me not put that in. We'll include that at the end. Now, we've been asked to find the CDT when the radius is 2 centimeters. So that means the CDT when R is 2 centimeters is going to be 3 out of 2 centimeters per second, which is 1.5 centimeters per second. So that would be our answer there. Okay, let's look at this example. All these examples are from the book Pure Math by Backhouse. So you could run to there to check them out. A horse trough has triangular cross-section of height 25 centimeters and base 30 centimeters and is 2 meters long. The horse is drinking steadily when the water level is 5 centimeters below the top. Sorry, and when the water level is 5 centimeters below the top, it is being lowered at a rate of 1 centimeter per minute. I'll just underline some keywords here. Find the rate of consumption in liters per minute. So the trough we're thinking of could be something like this. Say that's our horse trough, yeah? Now I'm just going to draw the cross section on its own. We have that its base is 30 centimeters and its height is 25 centimeters. Now we want the rate of consumption in liters per minute. So that's really the rate of reduction of the volume of the water within the trough. Now the volume of the water within the trough is going to be given by V, the volume at any time. T is going to be V times the area of the cross section, which is a half, times the base, times the height, times the length of the trough, which is 2 meters long. And so we can go with saying this is, by 200. Since at any depth, the length part of the water will always be 200. So I can say this is 100 BH. Now we have a problem because realize that this is in two variables, B and H. So now what do I need? I need an equation that sort of relates B and H so I can have this equation in one variable. Let me just draw an imaginary water level right there. So that was our water in the trough. Okay, so which equation could I use? The equation that I'm going to get is going to come from that. So if I have that as my B and I have that as my H, you realize that now I have two similar triangles. And B and H will always have the same, ratio. And we could go with B out of 30 would be the same as H out of 25. And so B will be 6 out of 5 H from this equation right here. And so because of that, I can write my V as 120 H squared. That's when you substitute B in this equation. So now I have V in terms of H. I can go ahead and get dVd, dVdH, and dVdH is going to be 240 H. What do we want? We want rate of consumption in liters per minute. So we want dVdt. We know that dVdt from the chain rule is going to be dVdH times dHdt. Now dVdH is 240 H and dHdt is what? Notice that the water level is being lowered at a rate of 1 centimeter per minute. So the lowering means that it's decreasing. So the rate of change there is negative and not and not positive. So this is going to be negative 240 H as dVdt. But now we want dVdt at a certain H value. Now, when the water level is 5 centimeters below the top, that would mean that this gap here, that gap indicated, would be 5 centimeters. And so what would be the depth of the water? The depth, there would be 20 centimeters of water. And so the value of H at that point, when the water level is just 5 centimeters below the top, the value of H there would be 20 centimeters. And therefore, dVdt, what would be calculated would be dVdt when H is 20 centimeters. That's going to be negative 240 times 20. That's going to give us negative 4,800 centimeters cubed per minute. However, the question wanted the consumption in liters per minute. And so this negative 4,800 centimeters cubed per minute would be negative 4.8 liters per minute. And so the rate, you could conclude that therefore the rate of consumption of the water is 4.8 liters per minute. Of course, the negative shows us that the water is reducing. And that's how we would get the answer. So this is how we work out rates of change using the chain rules.